So, yeah, these are the parts. Of course, there are some more software components involved in the whole process. Of course, one key aspect of securing network data is cryptography. We're implementing strong cryptographic algorithms in Spark, which for that special case, and this would be for a non-governmental scenario, this is AES and SHAT, the SHA-2 algorithm, and of course, and HMAC for integrity protection. We have proven the absence of runtime errors, and the good thing for our workstation scenario was that the performance of that crypto algorithms we implemented are pretty close to what OpenSSL, an open source crypto library written in C, is very close to the performance of that crypto library, and this is what we took as benchmark and used for optimization. This part of our project is released as open source and can be downloaded in its current release from that URL. The things we implemented for the actual IPsec protocol is the encryptor and decryptor I already mentioned. All traffic that passes the encryptor is encrypted using the AES algorithm, but only if there is a so-called security association is present for the traffic that was just sent. Every other traffic is discarded. For the integrity protection, we are always using HMAC SHA-512.256. And other things are important when you do IPsec, something like there's a sequence number increased at every packet that is sent, and an amount of the amount of information is tracked that can be sent over the wire. There are several limits in IPsec that limit the usage of cryptographic keys to mitigate crypto analysis. The decryptor gets the encrypted package, does an integrity check to prevent modification of the information. Of course, decrypts the packets if this was successful, and it does kind of anti-replay protection. That means this is also a countermeasure against crypto analysis and crypto attacks. That means no one must be able to put the same packet into that decryptor twice. The performance and compatibility is pretty good. The unoptimized version of the encryptor and decryptor that is currently used in our workstation has a throughput of 50 megabits for 2 instances. But as I said, we have not done very much about the performance yet. But these figures already are acceptable for our workstation scenario. You can run almost any thin client protocol over 25 megabits. This is no problem. It is compatible with IPsec, with the IPsec implementation of the Linux 2632 kernel. This is the counterpart we used for testing. And the very interesting point about the architecture itself is that it is very easy to integrate new protocols into either the black side or the red side. So should we decide to support PPPoE or some obscure protocol tomorrow, then we can just put it into the virtualized Linux and are done. Nothing has to be done with the security critical parts of the system. So this is the second case study I want to talk about. This is the multi-level graphics we have implemented. In a multi-level workstation, but somehow different classifications have to be handled, and there are many security aspects present. For example, you do not want to have a channel between different classifications. So an application with secret data and one with open data must not be able to transfer data from one classification, from one application to the other. You need some way for the user to distinguish different classification, which is commonly done through secure labels. So at some place of the screen, there is some label of which the user knows that he can reliably check the classification that is currently presented. And other points as denial of service. You do not want a client, an application of the system to be able to do a denial of service attack against the user or against any other application. Of Linux and the Xorg windowing system, just because we can get figures for it in terms of lines of code in contrast to Windows. A client, which is one of these, has to trust no less than 2.4 million lines of code. Again, a pretty conservative counting. One could take into account much more applications that may be trusted. So you have one client and another client, then there is the so-called X server, an application that's running on top of Linux. This, again, is written in C and uses the libc. And then, again, there's the monolithic operating system, for example, Linux, and it contains drivers, mechanisms for IBC, and so on. Again, all trusted code is written in C, and there's no formal modeling whatsoever. The question is, how can we transfer that architecture into something that is much more trustworthy? This is what we've done. We have implemented a native application which is called Console, which includes a graphics driver. And if we have some client which can be native as well as running on top of a Linux, these can access the graphical console through this graphics driver. That means they have some piece of memory mapped in by the separation kernel. These are completely disjoint. That means there's no way to access should be yellow, I guess. The yellow frame buffer by some red application. And this console application is implemented in Spark and also handles keyboard input. And so the user has what we call secure retention key that he presses, and then he can change between different consoles. And this switching between different frame buffer regions is done by this trustworthy console. And upon user request, after switching, all keyboard events are sent to the client that is then in foreground. And we also implemented the secure label which shows the user what the current active client is and what classification that client has. And we implemented a driver for the Intel GMA HD graphics chipset that is found on modern Core i7 notebooks, for example. And so we managed to only have the security critical functionality like switching and drawing the title bar inside this console, and everything else like doing the key mapping and doing the actual conversion of the graphics is done inside Linux, for example. We have implemented several drivers that enable Linux applications, for example, to see this as a standard Linux driver. So you can use your Linux applications on top of that secure console completely unmodified. And the performance is pretty comparable with a frame buffer on a native Linux. Although we currently do not support accelerated graphics. This is a completely different and complicated topic. How successful have we been? So we have to ask ourselves, how can we measure success of transforming monolithic architectures to Mills architectures? And I see two ways how to measure that. This is the TCB size reduction. This was one of our goals. And to measure the cost efficiency, how were the development costs. For the TCB size reduction, we measured both the monolithic system, the code size of the monolithic system, as well as the ones we implemented using the tool slug count, which counts the significant lines of code. And these are the results. about the TCB size reduction. For the IPsec ESP, I already mentioned the figures for the Linux kernel, something like 770,000 lines of code, C and assembly. And these are the figures for our components. The crypto library, libspark crypto, has 2,300 lines of code in Spark. Encryption, decryption, 1,300 Spark lines. Then there is a communication mechanism through shared memory, SHM stream, 260, and an AP to the separation kernel, 600 lines, and initialization. This is the only non-Spark part in our own application, 70 lines of code. And then the separation kernel has around about 10,000 lines of code currently implemented in C and assembly. So we end up with a total of 15,000, around about 15,000 lines of code for our trusted computing base of IPsec compared to that figure of Linux. And the graphics, if you make up the figures, again, the communication library, the console itself, 1,800 lines of Spark and initialization 70 lines. And again, of course, we have to trust the separation kernel, so we end up with 12,200 lines compared to the 2.4 million that you have with Linux and Xorg in the best case. That means we have a size reduction of 50 times in the IPsec case and 200 for the graphics. Costs, development costs for the IPsec ESP, total of around about 140 man-days for IPsec ESP, and I have to mention that this was one of our first Spark projects, and we hit the boundaries of the tool capabilities quite some time. So I'm pretty sure that with the next implementation would be much quicker than that, and 90 man-days for the multi-level graphics. So this did not cost us a fortune to implement those highly secure architecture of the multi-level workstation. Last slide, what we plan in future. Currently, we're doing an integration of Spark and the Isabelle theory improver from Munich University. We're currently at a point where we can parse and prove Spark VCs in Isabelle directly. That means we can read in Spark VCs to Isabelle. And what we're planning to do is model and prove security properties in Isabelle Hall and then show the correspondence to our Spark code we have written. There already was a proof of concept project in Munich with the RIPEMD 160 algorithm, which is a hash algorithm. The VCT tools, which also the expert will tell you about, was used. And we successfully showed that we could model RIPEMD in Isabelle and then show the correspondence to the Spark implementation. We are also playing around with generating Haskell prototypes of our software from the Isabelle model we have created. So this is another idea. We have to model the software in Isabelle, then create a Haskell prototype and play around to find out whether we have modeled the right thing. And we are currently planning and trying to get funding for an evaluation of this complete process in a bigger case study. And of course, we will continue with the development of our workstation. There need to be components for secure smart card handling, system control and configuration. This is what we're currently working on. We want to support virtualization of Windows in future versions of the workstation. Encryption is another future topic of research and development, and we have many more things on our agenda for the workstation. Okay, thank you very much.